Join us today as we explore reprofiling 22 long rifle rimfire bullets for flight improvement. This is the outline for our presentation today. I want to explain what reprofiling is, give some important background, talk about the procedures that we use, talk about testing and performance, and wrap up with conclusions. Bullet reprofiling is nothing more than changing the bullet configuration of the rimfire round. Our focus is on improving external ballistics for performance gains. Others are doing things like making hollow points. This is generally done with some sort of a punch and die sort of tool. On the left is the prototype we developed. Here's the punch. Here's an example of what the round looks like. And over here, we're showing examples of cases that have been prepared for measuring Brinell hardness. We know that lead hardness is extremely important in rimfire. We'll explain this more in detail in a minute. We would drill out the base of the case, empty out the powder, and then we can go ahead and test the hardness of the lead. This is what's called a crucible coin. So we melt down lead over here, and then we're able to monitor age hardening of the lead and make sure we can draw correlations. This is the Neal Waltz die that we went with. Here's the case holder, the die, which is beautifully made. This normally comes with both what's called the 10x tip and the hollow point tip, and on special request, Neal made us one for flat point. There are others, Pacos, Kelly's, Acu'rzr, D-Rock Kit, other do-it-yourself offerings, but we haven't any experience. This one here with the Neal die fits into the single stage press and is most appropriate for the kind of work we're doing. We want to point you to some of the reference material that we came across looking at reprofiling 22 rimfire. In the Frost book on page 27, he talks about the lead alloys used for making rimfire bullets and the associated hardness. Turns out that between 0.75% and 2% antimony is the ideal hardening agent for lead. He doesn't give a specific Brinell hardness, but certainly seems to have good information there. On page 130, he talks about bullet nose and heel characteristics. And although there's a amount of things that can be done with the bullet nose, he points out that the heel of the bullet, which we can't see from the loaded round, are very important. The most important reference, certainly a seminal development here, is what was done by the Ballistics Research Lab in the 90s by Robert McCoy. On page 1, he talks about project goals, and they're using Ely and RWS, and also ammunition being developed here in the US. They're able to change bullet configurations and charge weights, and able to test this with a very high level of precision. What was noted also is on page 1, he gets into the idea where this project came from. It came from the US Olympic teams wanting to develop US-made ammunition for rimfire instead of relying on ammo from Germany and England. Makes perfect sense. But as you can see, not really much came from that work. On page 4, he goes back and compares lead alloy, and he gives specific hardness. For instance, pure lead has a hardness about 4 to 5 Brinell. He's recommending that about 7.5 Brinell hardness is ideal. And he points out the research they did that by the time you get to Brinell hardness 10, you've actually lost the ability for the bullet to operate properly in firing. There's two other references here. We're going to talk about the PounderZ experimental methods. There's a video you can turn to, Intro to PounderZ, give you some background on that. And then also we're going to be using our models for PounderDrag, and there's a video there called LabRadar with PounderDrag you might find useful as you look at the information we present today. Are we breaking new ground here with reprofiling rimfire and creating flat points? Not really. Back in 2001, Ely introduced the flat tip on the 10X. Here's their comment that they provide. As it cuts through the air, its revolutionary design pulls the center of pressure forward, aerodynamically stabilizing the projectile and increasing accuracy at the target. So they certainly seem to be onto something, because 10x, match, and edge are all some of their top offerings that use the flat point. You'll notice something we call a pip on the front of the bullet. This is a little bit of a mystery. A couple of years ago, we talked to the technical marketing folks at the NRA show for Ely. They comment it's really just an artifact of how the bullet is manufactured, how it's swaged, kind of like the idea of an air hole, so you get a well-formed bullet. We appreciate the proprietary work and all the development effort that goes into ammo, so we really don't hold them to that, and so for us, the little nose pip remains a mystery. When we measure the overall coal without the pip, we come up with 0.960 inches. In 2018, SK, a Lapua company, added 2 flat nose bullets to their lineup. You can see from their comments, pretty modest what they say about this. We noticed that there isn't a pip on the nose like there is with the Ely. When we measure the coal, it comes out 0.960. The 2 lines are the match and the basic. In this study, we're focused on the basic. We tend to hold off quoting prices because such things change so often, but just for a benchmark, we use the standard plus for the work in this presentation. So benchmarking that at say $6.50 a box, the flat nose basic goes for $7.50. So it's really just a 15% premium. So just something to keep in mind as we go forward and talk about performance and results. SAMI maintains 2 specifications for .22 long rifle, one for sporting arms, the other for match. The difference are in the chambers. The cartridges are the same. Notice in their diagram here, specifications are given in engineering style. We do statistical work. We convert those into lower spec limit and upper spec limit. Here are the 5 key specifications that come into play when we do reprofiling. Notice that for both the me-play and the ogive, there aren't any specifications given. Let's look at the changes that will be made when we do reprofiling. Using the Neal Waltz die, the coal will be precisionally reduced based on the die setting. We're going to create a very distinct me-play. The ogive is free to broaden, and the cannelures will broaden to the die inside diameter, which in our case is 224 thousandths. This will also have the effect of moving any bullet out around this and probably improve its match chamber fitment, although we haven't done any testing on that. But it's important to keep in mind it's very, very easy to overdo. It takes very little force to do this, and it's easy to overdo. It's important to start with good quality ammo. Our goal is to make good ammo a little better. Ammo lots need to group at least 1/4 inch 50-yard CEP to be considered. Here are 4 of the suppliers that fit that bill. We wish they were more domestic, but you can determine this for yourself and go from there. We need to measure rim thickness, sampling a brick, and the sampling there can be generous depending on how precise you want to be. We use the rim thickness tool. Here's a photograph of the tool we designed and built over about 15 years ago. After we record the data, we run an X-bar in our control chart and use what we call the X-bar rounds to set up the press. We'll explain a little bit more about that in just a minute. The setting up the press is very simple. You install the .22 shell holder, install the die, run up the ram to the die base, lock the die, load and raise the X-bar round, dial down the punch until touching the bullet, back down the ram, scooch down the punch, and relift the ram. Measure coal, repeating until you get the length desired. In this case, 960 inch. Secure the punch locking ring, periodically check the next few rounds, and you're good to go. Since remember now, .22 bullets have external lubrication, so over time keep an eye and clean out the die as appropriate. For match level performance, measuring and sorting off of rim thickness has been around for a long time. For the 22, the rim head spaces the cartridge, but when we do our reprofiling, it's going to be based on the overall length of the cartridge. So what we like to do is find the average rim thickness and set up our press, so then the variations will be around that average. A good way to do that is with the control charts. These are important in their own right, and they have many applications in reloading and shooting. For instance, checking lot-to-lock performance of rim thickness or even muzzle velocities. And this is an easy way to get the average rim thickness. It's going to be this value right here, which we call X bar. And we know from this slot it's at 42 thousandths, which puts us just a scooch under the upper limit of 43 thousandths for the SAMI spec. And we have the range, the X bar here is right around about 1/1000th of an inch. So we're going to want to set the press up using the rounds that are closest to 0.042. Let's take a close look at these rounds. Here we have the Ely edge, and you'll see the little pip on there. Here is the 10x tip from the Neal Waltz. You'll notice that that's a little broader. These two here are profiled to 9500. These three are to 9600, and then these two are the flat nose basic. You'll see that here the knee play is actually wider than the 960s, more in line with the 950s. But when you look at this in profile, you can see here what the Ely edge looks like, and then here is the 10x punch with the Neal Waltz. You'll notice the shape of the ogive is a little different because everything isn't scooched down. It actually has room for the lead to go up into the pip. You can see the difference between the 950s and the 960s right here. That difference is only 10 thousandths, but you can see it. And then notice also now on the SK flat nose. So even though it's the same coal, here you notice a distinctly different shape of the ogive and a flatter knee play, even when compared over to the edge. So definitely there's difference between all of these rounds, and creates for some interesting study. Here's our experimental setup. We're going to use the Neal Waltz flat nose punch. We're going to use the SK standard. We're going to use the same lot. We're going to make a box of 960, a box of 950, and then at the 50-yard range, you're going to use the PounderZ 5X group by method. We'll do one of the targets using the standard XK, so think about it as a control or a baseline, and then we'll do one with the 960, one with the 950, and then we'll go ahead and do one with the SK flat nose. We do our analysis, then we go back at 100 yards and do PounderZ 10X groups of both the SK standard, our control, and the best of the coal reprofiled rounds. Here's the equipment and range details. We're going to be using the CZ457 Precision Varmint Trainer, 24-inch barrel, 1/16 twist. We're going to be using an indoor range, 100 meters. We'll have target stands at 50 yards and 100 yards. We're going to be on a solid bench rest, so we're going to be taking vibration and wind out of this and using bipod and rear bag. For range instrumentation, we're going to be using the LabRadar and the WeatherFlow weather beater. For analysis, we're going to use our PounderLab models for calculating out air density and speed of sound. We'll be using the OnTarget software TDS for measuring targets, analyzing data there, and calculating the CEP. And we're going to use the PounderDrag models for calculating the coefficient of drag and ballistic coefficients, the flight analysis part of this. And then to model the target hits, we're going to use the PounderLabs simulation for the Know Your Limits. Here's the 50-yard workup for the two reprofiled rounds. Here we have the 960 on this side and the 950 here. We'll provide summary information in a minute, but the reason we wanted to show this is that all too often when you lay out all of these bullseyes and just go shooting at it, you might start thinking this is all the same thing. But once you start to really do it analytically and looking at the statistics, you actually find out these things are different. For the 960s, the average CEP is 0.175. And by the time we go to the 950, it's opened up to 229 thousandths. So it might not seem like much looking at it visually, but statistically, it's a pretty big difference. Here's the PounderZ workups at 100 yards. On this die, we have the standard plus. You'll notice that the dispersion is pretty uniform. You see from the standard deviations, they're approximately equal, which is pretty typical for this ammunition. And for group size, you're sitting about 1 MOA. On this side, you can see very distinct clustering. We're using the 960 rounds. There's some asymmetry in the distribution, but you'll notice two distinct different clustering here. There's nothing unusual about clustering generally, but to have clustering this profound at 100 yards is pretty significant. And you can see the CEP of the standard SK Plus is about 425 thousandths, and over here for the 960, that's dropped to 360 thousandths. Here's the LabRadar trace data for our control round, the SK Standard Plus. A couple of things to point out. First of all, the y-intercept is equal to the group average muzzle velocity, so this is going to represent the group real well. Also, we have good clean data all the way down to when the bullet hits the target and backers. The LabRadar can see the flights of the bullet behind the backers, but you can kind of see that that gets scrambled pretty good. So that's again pretty typical. Here's our velocity equation, and we can tell from the coefficient of determination we've got a real good fit here. Here's the summary data for our shooting sessions. Ranking these by CEP, the 950 is lower performance over our standard control. We see the 960 is an improvement, and we even see a greater improvement with the flat nose basic. These standard deviations are fairly typical. When we look at 100 yards, the control is at 425 thousandths, but we have improvements to 360 thousandths for the 960. Muzzle velocities for the group, 306, these are pretty comparable. And looking at these with the Mach number, again, very, very close. The standard deviations of the velocities are reasonable for these rounds and not distinctly different. When we've done the analysis, we see that the coefficient of drag are pretty comparable. We're only different in the third decimal place. I'm not really sure that's significant. And we go through and calculate the ballistic coefficients for RA4 as well as the standard G1 model. So we are not going and doing any deeper analysis with gyroscopic stability. We think that although from a target hit point of view, we see improvements, but we're having a little trouble here seeing if we can do the velocity analysis to justify that. But at the end of the day, how that bullet hits the target is really what it's all about, and we'll continue to study this further. Let's look at these results as they might apply to practical shooting. Let's use, for example, the Know Your Limit array for rimfire. Here's a picture of the array. This is normally out at 50 yards and consists of 8 swingers with the disc starting at 2 inches and going down 1/4 of an inch at a time. The scoring on this is at targets 1 through 4, generally 1 point. The tougher targets at 5 through 8 are 2 points. So if you don't take a shot at those last 4 in a 100-point match, you're leaving 8% of your score on the table. So that's something to think about, because the generous scoring on this is when you miss, you just lose the point next to the one you took a shot at. But the punitive scoring is if you miss, you lose everything. So you'll have to evaluate the risk of just how far you want to go in the array. Well, This is a simulation we've developed to kind of show you how this would work for the data we've done. So you can see here, this is hit probability based on the CEP as a function of target radius. For all the ammo, you can see that the first 4 are pretty much gimmies. But now things start to get sorted out. We can see over here, the 950 did the poorest. Here's what we normally see for the SK Standard Plus. And then here's the improvement we see at 960, and here's the flat nose basic. So the idea you can see from the table, when you get down to the 1/4 inch target, you have a 17% chance of hitting it with the 950. That goes up to 22 for the SK Standard Plus, and the 960 improves that to 28%, and the flat nose improves that to 37%. So of course this is just a simulation based on this data. Whether you're shooting this on the bench with bags, prone with a bipod, or offhand on a barricade, or if you just ran 50 yards from the last stage, all factor into what you can actually do. But you want to try to look at your platform and your ammo so you know where you sit and what they're capable of, so you can focus on your shooting skills and your environmentals during the match. Here's our takeaway from this investigation. We think there's some benefit to reprofiling the 22 rimfires. We think we can take good ammo and make it a little bit better. Certainly the gains in shot and group precision might be small, but they're measurable. And we find this is easy and fast to do with the Neal Waltz Die. Along the way, we might have dispelled a few of the myths too. I think we've demonstrated that flat nose rimfire isn't just a marketing message. We think there's actually something there, and certainly Ely and Lapua are making investments. The flight stability and hit performance, we see gains all the way out to 100 yards, and we haven't seen any downsides with bolt action rifles. Now for semi-autos or lever actions that might be a little bit bruise the tips of bullets, a little harder on the nose of these things, you'll have to kind of investigate that and see what those challenges might be. But the takeaway here, small gains can make a competitive difference. Remember, nothing is in shooting is a once and done. You have to revisit these things and work on them all the time. And if you want to look into reprofiling or perhaps buying some of the commercial, we suggest you take a look at it, investigate it, and see how it might improve your shooting and your competitive situation. And as Jeffrey says, you make the call. This completes our presentation, and as you're thinking about subscribing, please look over these important notes and disclaimers. They're here for your protection and for ours. Thanks for watching. See you soon.